Thank you. Thank you. Pretty nice to be here. I think it's been like 9 or 10 years since I've been here. I'll mention that I first came here for DIMACS REU, like a research experience for undergrad. So I was an undergrad in 2007. I was giving talks in this room. Yeah, it's been a while, I think, for 2007, 17 years. Wow. Good. So today, I got 2 hours to talk to you guys. So here's the plan. I'll start talking about, I've split the talk roughly in 2 parts. The first part will be mostly an introduction to average distortion embeddings. I'll tell you what they are, and I'll tell you a little bit about how to construct them. So that's the first hour of this talk, of this tutorial. I've tried to keep some balance between not being too technical, but I also wanted to show you a little bit of how some constructions at least work. There's a lot I won't be able to cover, and I should say there are people in this room who are much bigger experts than me in this, and they can help me if I get something wrong. The second half of the talk will be kind of different. So in the second half, I'll try to give the flavor of how to use average distortion embeddings for one application that they're useful for. In particular, how to use them to construct data structures for approximate near-neighbor search. So this will be after the break, mostly probably. That part, I'll show fewer details and there will be a little bit more hand-waving, but I wanted to give you kind of a slightly high-level picture of how these mathematical objects that we'll construct in the first half can be used for algorithms and data structures. Okay, so that's the plan. There's some really cool open problems that I'll share and we can also talk about in the afternoon. Okay, stop me at any time with questions. So let's get started. I'll start very, so I wasn't, it's a little hard to target this. I'll start with very basic things that for some of you will be maybe for most people will be too basic, but I was expecting maybe there will be some people who are new to this in the audience, and I also just wanted to fix notation and kind of fix terminology. So I'll start with really basic stuff. What is a metric space? Okay, just to fix some definitions and notation. Let me just make sure that you can see. Okay, good. Yeah, let me know if you cannot see or read anything. Good. So these entire 2 hours we'll be talking about metric spaces. Let's just kind of make sure we all know what a metric space is. These are the axioms of a metric space. I won't dwell on this because I do expect it's familiar to essentially everyone. Again, this is just a way to axiomatize what it means to measure distances. So a metric space is some set with the distance defined on it. The distance is what it sounds like. So it assigns a non-negative number to a pair of points, and it must satisfy these 3 properties, which again I think what you would write down if you try to write down axioms for what it means to be a distance. So the only way to have distance 0 is if the 2 points are the same, the distance is symmetric, and I guess the most interesting one is the triangle inequality. So if I'm looking at the distances between 3 points x, y, and z, basically what happens in the Euclidean plane must happen in the metric space, which is that the distance from x to z should be at most the sum of the distances from x to y plus y to z. Okay. So that's a metric space. Maybe I'll give one example, or 2 examples. This is all kind of meant to generalize Euclidean distance, but it also captures many other things. For example, shortest path distance in a graph. Okay, so this is a very general kind of object. Something a bit less general is and a little bit different is a norm. Norms are one way we get a lot of metrics. So a norm, all my norms will be defined on like d-dimensional real space. So a norm is a way to measure the length of a vector in a vector space. So a norm satisfies some properties that are kind of similar to the properties of a metric. Again, this is a function that I'll usually denote like this with these like double bars. It assigns a length to any vector in a vector space. For me, the vector space will always be R to the D, so d-dimensional real space. It satisfies, again, similar axioms. The only vector with norm 0 is the 0 vector. It scales as you expect when you scale the vector, and it satisfies this kind of thing, which is basically again the triangle inequality. So the length of a vector, maybe I'll draw the picture again. So if I have a vector, one vector x and another vector y, the length of x plus y should be at most the length of x plus the length of y. And now every norm defines a metric on this vector space, and the metric is just the norm applied to the difference of the vectors. Okay, so this is one way we get norms. Here I want to introduce a couple of examples of norms that I'll talk about over and over again. So one is the LP norms. I'll write them like this, LP to the D. This is the LP norm applied to R to the D. And here the norm, which I write like that, with subscript P, is this. Okay, so I take every coordinate, take its absolute value, I raise it to the power P. And I take the 1 over P power of this sum. This is a norm for P greater than 1. Maybe some special cases, L infinity, where I just take the absolute value, the maximum absolute value of any coordinate. And one more example that I'll mention a few times is Schatten-p norms, which is basically the LP norms applied to the single values of a matrix. So here, so I lied a little bit. I said that all my vector spaces will be R to the D. For Schatten-p norms, the vector space is the space of, say, D by D matrices. And the norm of a matrix, which I write like that with SP, is basically the LP norm of the singular values of the matrix. Here, M is a D by D matrix. And this is the singular values. All right. This turns out to be a norm that's verifying the properties is not hard, but it's also not completely trivial. Okay. All right, so these are the basic objects that I'll talk about. Let me mention one more simple thing that will be useful. So there are many ways to take metrics and derive new metrics from them. I won't try to I won't really mention any of the constructions except one here, which is a very simple construction. This is which is this one. It has some connection to like these nice fractal pictures. Okay, so it turns out that if I take a metric and if I raise the distance function to some power between 0 and 1, I get another metric. Okay, so if I take a metric space M and I get take the same metric space on the same set, but I raise the distance function to the power omega for some omega which is between 0 and 1, then that also satisfies the triangle inequality and all the properties of a metric. It's a relatively simple exercise to to verify the triangle inequality still holds. It's called the omega snowflake of a metric. So this is one simple way you can take a metric and derive new metrics from it. As far as I know, it's called this, and like again, maybe Asaf can correct me or something like that. I think it's called a snowflake because this picture is the Cox snowflake, and I think the Euclidean distance on the Cox snowflake is a snowflake with some power that I forget right now of a different metric. Is that correct? Anyway, so you get these like weird geometries when you do this, even though it's a very simple operation. It does weird things to the metric in some sense. And I should say, for example, take a metric that I get from a norm and I take the snowflake of it, I don't necessarily get a metric that can express from a norm anymore. Okay, so it does like enrich the types of things you can do. Okay, so you'll see how we'll use this later. For now, it's just a definition. Questions? All right, good. So this tutorial is supposed to be about embeddings. So I'll start with the notion of embedding that's probably familiar to most people. So, and from a computer science perspective, you can think of this as kind of a reduction. So over the years, over decades, we've developed some algorithmic tools that help us deal with, at least with some special metrics that we understand better, like being Euclidean distance or Manhattan distance. What do we do with the other metrics that we don't necessarily understand so well? One approach is to try to do basically reductions. Try to take our metric space that we're trying to do something with, either prove a theorem or design an algorithm, and map it to a metric space that we do understand, and then run whatever algorithm we know how to like design and run in the metric space that we do understand. Okay, so one kind of reduction is given by these objects, very natural objects called bi-Lipschitz embeddings. Okay, so this is basically a map between metric spaces that, roughly speaking, preserves distances up to an approximation. Okay. So here's the definition. What is now an embedding? It's a function that maps some metric space to another metric space. Think of this as something nice, like think of this as, for example, Euclidean space. Okay, so think of n as something nice, right? Okay, and what do we ask from this function that maps our metric space that we're trying to somehow understand, but maybe we don't really understand so much? It maps this M into Euclidean space in a way that approximately preserves distances. In particular, let's ignore this lambda for now, and for the most part we can ignore it. So ignoring this lambda, what does this say? It says that no distance expands by more than a factor d when I apply this map f, and also no distance contracts if no distance contracts. So annotate this. Distances expand by most d factor, and distances don't contract. Okay, and I have this additional factor lambda, which is mostly a technical thing. It just allows us to scale things. Like this factor lambda is there because if I can take my metric space and just divide every distance by half, and I still get a metric space. And I want to say that this is effectively the same metric space. And this is what this lambda is there for. Okay, so for things like metric spaces that come from norms, this can be ignored. This lambda can be ignored. Okay, so this is if someone just says I have a distortion D embedding of something like Earth mover's distance into Euclidean space, that's what they mean usually. Okay. So let me give just like very briefly some highlights about. So there's a lot I can say about bi-Lipschitz embeddings. I could read a lot I can say about bi-Lipschitz embeddings. I won't say much. I just want to give you like a little bit of a flavor of the kinds of things we know. But there's a lot that I'm not saying, and because this is a tutorial, I haven't been very careful with citations. I've mostly given citations to like newer work. I haven't given a citation to like Frisch John, for example, here. So think of this as more of a lecture, but I can, if you want to know the citation for something, I can find it. Okay, so here's one very classical thing that we know about embeddings. Very basic important fact, John's theorem. One way to formulate it is that any d-dimensional norm space embeds into Euclidean space with distortion square root of dimension. Okay, so this is potentially very useful in low dimensional settings. For example, in dimension 2, it tells us that in some sense, all norms in dimension 2 are within square root of 2 factor from each other in terms of like there being embeddings between going between them. All right, and the square root of d factor cannot be improved in general in terms of the minimum distortion that it can achieve for a bi-Lipschitz embedding. This is tight already for L infinity, not L2. This is silly. L1. Yeah, this is a typo. This is tight for L infinity and L1. Okay, and this I won't use this, but I mean I won't use this picture, but I want to show you this picture for maybe the few people who haven't seen it. This comes from a very natural geometric fact about approximating arbitrary symmetric convex sets by ellipsoids. Okay, so and this is what some of you may have heard as John's theorem also. So what Frisch John proved is that any symmetric convex set can be approximated up to a factor of square root of d by an ellipsoid. What that means is this, or this is how it connects to the statement about embeddings. So if I take the green thing to be the unit ball of the norm that we're embedding, then John's theorem, what it really shows is that there is like a linear image of a Euclidean ball that I can fit inside. So this is some linear map T applied to the Euclidean ball. This is Euclidean ball. Okay. And then if I scale this ellipsoid that I get by applying this linear map to the Euclidean ball by a square root of d factor, I end up with something that contains the unit ball of the norm. Okay, so I can find an ellipsoid that's contained in the unit ball of the norm. If I scale it up by square root of d factor, it contains the unit ball of the norm. So this is square root of d times the same ellipsoid. Okay, and the embedding is in fact linear. The embedding is just the inverse of this. It's just the inverse of this map that gives us this this ellipsoid that approximates the unit ball of the norm. Okay, so if one takeaway from this is when you're talking about metric spaces that come from norms, usually you can reduce the questions to questions about the unit balls of these norms. Like the unit balls of these norms capture like all the information you need about the norm, and often questions about like the geometry of the norm space can be reduced to nice geometric, well, I don't know how nice, but to geometric questions about convex sets. In particular, questions that have to do with the unit balls of these norms that you're trying to understand, okay, which are symmetric convex sets. All right, so that's one basic embedding result in some sense type. sometimes, so we said this is tight for L1, right? So it sort of says, well, I cannot approximate L1 by Euclidean space with the bi-Lipschitz embedding any better than square root of D factor. Okay, but that's missing something because there's other things I can do. So I can take the half snowflake of L1, and that embeds isometrically into Euclidean space. So in other words, there's some function f, so that I can apply to my vector space Rd, right? So that after I apply this function, and I take the Euclidean norm squared, that's exactly equal to the L1 norm before I apply the function. So in some sense, L1 actually can be approximated very well by Euclidean space. You just have to kind of square the distance or take the square root of the distance, depending on which side you're doing it. Right? Remember, the snowflake means that I have to put a square root here. Here I've just squared things. Okay, so this snowflaking does give us more power, and this is often quite useful to do that, algorithmically as well. So in some sense, for algorithmic applications, taking snowflakes usually doesn't come at a huge cost, at least as long as this half doesn't become too tiny. However, snowflakes don't always help. So if I look at the other tight example from John's theorem, which is the L infinity norm, this maximum of coordinates norm, even if I take a snowflake, that doesn't help me too much, unless the parameter of the snowflake, the power I'm taking, becomes too tiny. If it becomes too tiny, that also would cause problems for applications as well. Intuitively, you don't want this to be too tiny, because usually downstream it would lead to worse results in terms of approximations. Okay. Good. So the exact result is that even if you take, let's say, a half snowflake of L infinity, you still need polynomial distortion in order to embed that into Euclidean space. Okay, so that by itself doesn't help if we want to go beyond John's theorem. All right. So this is essentially all I'll say about bi-Lipschitz embeddings. I'm also trying to motivate the actual thing I'll be talking about, which is average distortion embeddings. But there's a lot more that I can say. There's tons of very well-known, classical, very useful results about embedding finite metric spaces, embedding doubling metrics, embedding Earth mover's distance. And there are very nice write-ups about some of these results out there. I can point you to resources if you want to learn more. Good. For now, for me, here's the question I'm interested in. Can I, let's say I restrict my attention to d-dimensional norms, and I want some tool that allows me to reduce working with d-dimensional norms to working with something that I understand better, like Euclidean space. Okay. John's theorem provides one such tool, but then I'm stuck with this polynomial in dimension embedding. Polynomial in the dimension distortion. Okay, so I get pretty bad approximation factors in high dimensions, and that's I guess the topic of the workshop. We want tools that work in high dimensions. Turns out that taking snowflakes sometimes helps, but not always. So that by itself won't fix the problem. So we'll try to do something else so that I can still reduce d-dimensional norms, even when d is high, in a useful way, to something nice like Euclidean space. And for that, I need to introduce a new tool, which is mostly what I'll be talking about from now on, which is average distortion embeddings. So this is a relaxation of embeddings, of the embeddings that I was just talking about. It's a very natural relaxation. I'll show it in a second. It turns out to be still useful for applications, which I'll try to convince you of probably after the break. Okay, so here's the definition. Here is what is an average distortion embedding. You can see it as a definition of average distortion, which is a measure of how good an embedding is. I cited Rabinovich for this definition. I think that's this paper by Rabinovich from 2008 is where the earliest reference I've found for this definition, although I'm not 100% sure that it hasn't appeared before. Okay, so definition is very natural here. From now on, since I'm most interested in norms, and I'm definitely most interested in embedding into norms, like in particular into like Euclidean space, I've written the definition to be about embedding a metric space into a norm space, in which case I don't have to deal with that lambda thing anymore. But this makes sense more generally as well. Okay. Good. And the definition is almost exactly the same as the definition of bi-Lipschitz embedding. Remember, for bi-Lipschitz embedding, we wanted to make sure that, okay, so what is the definition? Sorry, I'm like this is, let me back up and like make sure this makes sense, because it's the most important definition for this like next, many minutes. Good. So again, this is a relaxation of a bi-Lipschitz embedding. And it asks the following. So we say that some metric space embeds into some norm space, think Euclidean space, with average distortion D, if the following is true. I want that for every finite point set P in the metric space, there exists a map. This will be the embedding. And this map can depend on the point set P. Okay. And what I ask from this map is the following. First, I ask that distances don't expand by more than a factor of D. This is the exact same thing as bi-Lipschitz embeddings. However, on the other side, I'm only asking that the average distance between points in P after I map them is at least the average distance between points in P before I map them through F. Okay. So again, what I want is that if I choose, or like if my adversary chooses any point set in my metric space, then I can come up with a map that doesn't expand distances by more than a factor of D and doesn't contract distances on average over this point set P. Notice the first thing should hold for every 2 points in the metric space. That's important, at least for my applications. And the second, the second condition must only hold for the points at P, but again, the function can depend on P, and that's important. That way, helps a lot. Like if the function did not depend on P, then this would be basically, probably would be the same as average distortion embedding. It would be the same as a bi-Lipschitz embedding. Slightly different from like other definitions, but I think it's equivalent, and it is the one that I need. And I think it's like formally equivalent to other definitions you may find. Like here, you may wonder, why is it for every finite set P? Maybe I should just make it for every like probability measure on the metric space, and yeah, that's equivalent, and you can also ask that. And but for algorithmic applications, this is the one that I need. Good. Yeah, so in the second half of my talk, I'll try to convince you that this is useful for approximate near neighbor search data structures. It turns out to be also, and I think this was Rabinovich's motivation, it turns out to also be useful for other things like approximation algorithms for sparse scaling, for example. So does this make sense? This is an important definition. It's already interesting if like M is a finite metric space, I can take P to be all over M, and this is already like an interesting definition. Good questions? No? All makes sense? Okay, so to make this interesting, there better be more I can say about average distortion embeddings, like better things I can say about them than I can say about bi-Lipschitz embeddings. Like it better be the case that I can achieve smaller distortion. That's what I'm saying. Right? Last chance to ask a question. Yes.
Does this need to hold also for multi-sets? So like if you have weights on the
yes, let's say that P actually can be a multi-set, yeah, that I can take multiple ones. And yeah, I also wanted to keep this technically a bit simpler, but it's very natural to define it just for any like any Borel probability measure on the metric space.
I guess if it would be for multi-sub, then I guess it would reduce to like exactly distortion, isn't it? Because you would just take multi-sub, which actually has the same point like that.
Oh, good. But the map can depend on the multiset.
Ah, okay. Thanks.
Yes, that's very important. So constructing an average distortion embedding looks as follows usually. Like I give you the point set. For our data structures problems, the point set will be something related to the point set that we are storing in the data structure. So I give you the point set P, and then you give me the map F that achieves good average distortion. Okay. So the order of quantifiers is important. Like for every P, there exists a map as opposed to the other way around. Good. Okay. So again, some highlights. I should say results, but you know, I said results here, but again, it's my highlights. As in, I'm not claiming this is everything I can say about average distortion embeddings. This is just something that I will say, that I chose to say. Good, so I'll start with a result that I find very surprising. This is due to a sub Naor. It says that the half snowflake of any d-dimensional norm space embeds into Euclidean space with logarithmic average distortion, square root of log d. Like contrast that with John's theorem, right? John's theorem says that you can achieve, for a bi-Lipschitz embedding, you can achieve square root of d. That is the best possible. If we add snowflakes into the mix, you can do a little bit better, but not much. Again, you'll be stuck with like polynomial in d dependence in the distortion. But somehow, if you take a half snowflake and you allow average distortion, you can achieve this logarithmic distortion. I'll say something here, which is already pointing to like an open problem, which is that sorry, something's wrong with my pen. 1 second. So this embedding is non-constructive in the sense that we don't know, like, it's also not explicit, and we don't know anything, we don't know in any sense, efficient algorithm that can compute it. I mean, if I talk about efficient algorithms, I have to say, how am I providing the norm space to you? And the standard way would be to give you like some sort of oracle that evaluates the norm, and maybe a few extra technical guarantees. But there's nothing like that. Like, there's no natural assumption under which we know how to compute this embedding. So Naor's proof uses duality in a way that makes it hard to see what the embedding would even look like. Okay, so that's an interesting, like that suggests immediately an interesting open problem. Okay, some more results. So remember already for John's theorem, LP spaces gave like tight examples, but here we can do even better than this general result for LP spaces, at least for not too large values of P. So for any P, the d-dimensional LP space embeds into Euclidean space with average distortion on the order of P. Okay. So if P is not too large, this is great. And I'll try to show you something similar to this with an explicit embedding. The first result here also didn't give an explicit embedding, but we now do know explicit embeddings that achieve this. And they're also like efficiently computable. Okay. Good. So, by the way, these references, I'm not sure those are exactly the right references, but you can definitely find these results in these places. So the Schatten-p norms, remember these like LP norms, but applied to the singular values of a matrix, satisfy very similar guarantees. Actually, they can also be embedded into Euclidean space. So the Schatten-p norm can be embedded into Euclidean space with average distortion, again, on the order of P. And how efficient these are, yeah, they're definitely explicit embeddings here, but there's still something inefficient about them. I can talk more about that maybe during like open problem session. Okay, and this is for P greater than 2, both of these results. For Schatten-p, okay, for LP and Schatten-p also you can get constant distortion for an appropriate like, snowflake of the space. Okay, good. So hopefully this is convincing. There's like a lot of, this is not everything, by the way. Again, this is just some highlights. Hopefully this is convincing that there's things we can do with average distortion embeddings that we cannot do with bi-Lipschitz embeddings, in the sense that we can make the distortion lower. Of course, that's only useful if we can also use these embeddings for something interesting, which we'll see later.
So,
Okay.
the dimensions are not important here?
When I say Euclidean space, yeah, so, right, that's exactly what I was trying to hide is the dimension. For a, good. So, often the dimension is not too important. Of course, for like algorithmic applications, you don't want it to blow up too much, but usually that's not a problem. And for these guys, actually, the dimension, I think, doesn't even change. Here we have to be a little bit careful. But something like Johnson and Lindenstrauss, like dimension reduction would at least should be able to get you, or maybe not even that complicated. Yeah, it should be possible to say something explicit about dimension, but I haven't thought about that. Here, I'll show you some constructions and the dimension doesn't even change. Okay. Yeah, like Euclidean space is usually like nice enough that you don't need to worry too much about dimension. Okay, so good. This is the definition. This is kind of to motivate that something new is happening here. Like there's something different here compared to bi-Lipschitz embeddings. And with the rest of the time I have before the break, I mostly want to show you the flavor of one construction. How much time do I have actually?
How much time do you need? 15 to 20 minutes?
Perfect. Good. Okay, let me do that. All right. So let me now say what I will show you. So I'll talk about this. So what I'll do in the next however many minutes I need, I guess. We'll see.
Quick question.
Yes.
So what's known for general d-dimensional norm spaces?
So this is for d-dimensional norm spaces. So there's like a non-constructible, like there's an embedding that we know exists, but the proof is via duality, so we don't know what it looks like. It says that the half snowflake of any d-dimensional norm space embeds with logarithmic distortion. This is generally tight, I think, for L infinity. This is tight for L infinity again, it turns out. The half snowflake is also necessary there. So you do need, like, if I don't do that, then I think I'm stuck again with polynomial distortion. On
Even
average.
1/2 plus epsilon.
Sorry?
Even 1/2 plus epsilon.
1/2 plus epsilon.
Anything.
I see. Right. So, I see. Right. So Asaf is saying it's not just that I need some snowflaking. I actually need it to be half. If I go a bit above half, it's not enough.
I see.
Yeah. So I'll mention at the end. Hopefully, I have time. This is quite non-explicit. We know some more explicit embedding for any norm space with kind of worse distortion guarantees. So when we talk about explicit, let me go back to the definition. There's like a couple of things I can ask. One is that if I have this f, and I give you a point x that I can actually compute what it embeds into quickly. I mean, okay, one level of explicit is I can write it down like somewhat explicitly. That's a bit vague. But in terms of complexity, one thing I can ask is once I have f that I can compute f of x, another thing I can ask is that, well, once I have p that I compute what this function f is. And there's some cases where there's something that we don't know how to do efficiently in terms of computing f, but the f can be written down in like short amount of space and can be computed quickly once I write it down. So there's like these kind of subtleties in terms of making things efficient. And there's like, again, open problems there. Okay, so next what I want to show in the remaining time is fairly explicit, efficient embedding LP to the D into L1 to the D with average distortion on the order of P. Okay, I'm showing L1 to the D instead of Euclidean space, but everything I'm showing works into Euclidean space. It just like some things are slightly less technical, so I chose to do it into L1. So embedding into L1 is like it's a richer, I don't know, target. So it's a bit easier, a little bit easier. In this case, it doesn't matter too much actually. Okay, good. So let me show you what goes into like one construction of an average distortion embedding. There's a lot of nice stuff that I won't be able to say, by the way, that just for the sake of time. But there's like a beautiful connection to nonlinear spectral gaps, things that are really nice, but I won't get to. So I'll give you kind of the most concrete constructions that kind of lead to efficient algorithms. That's the choice I made. Good. So again, I'm trying to build an embedding of LP into L1. So what could I even do? How do I embed LP into L1? And here is like a very simple classical construction. This is the Mazur map. I guess it's due to Mazur, but I actually don't know the history. But it's a classical function with nice properties. The idea is very simple. Trying to map LP into L1, and again, yeah. So everything I say will actually work. Will work for like any LP for P bigger than 1. Finite P, I guess. Okay. So again, it is very simple. I'll just raise every coordinate to P, roughly speaking. Okay, and I'll preserve signs, which is I think also like the natural thing to do. I take every coordinate, I take its absolute value, raise it to the P, and I multiply by the sign so that negative things stay negative and positive things stay positive, but the magnitude gets raised to the power P. Okay. So that's the Mazur map. You just do this separately for every coordinate. One thing that's nice about it is, okay, think of it as a map from LP to L1. So what is the norm of this map applied to some x? Yeah, good. So what is the L1 norm of MP of x? Which again is that's NP.
P norm to the power of P.
The P norm to the power of P. Right? If I just compute the L1 norm of this now, in the L1 norm, I'll take absolute values, so these signs drop off, right? So this is just x1 to the p blah 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 plus xd to the p, and this is just the LP norm to the power p. Good. Okay. So in particular, this is a map that takes the unit sphere of LP and maps it to the unit sphere of L1, right? Because if x has LP norm 1, then M of x would also have L1 norm 1. Okay, so this maps the unit sphere. Unit sphere just means points of norm exactly 1. Okay, it does it in kind of a nice continuous way. Good. So, so again, it maps unit sphere to unit sphere in a nice continuous way. How continuous? There's ways to measure that. Sorry, it's a bit of a heavy slide. Just focus on this for now. Let's focus on this. Good. So this is kind of an estimate that tells you how continuously does the Mazur map one sphere to another. That is, how continuous is this function? Okay, so it's almost like it almost doesn't expand distances by too much, right? But there's something a bit off. The thing is, because of this raising to the power p, the left-hand side is like homogeneous to degree p. And it kind of, that causes trouble in terms of making sure it doesn't expand distances everywhere, right? Because it raises distances to the power p in some sense. So that will like cause trouble for like large distances. But something similar is true. Basically, it doesn't expand distances on the sphere, is one way to think of this. So let me do this. So for example, if I take 2 points x and y of LP norm 1, and this inequality tells me that after I map them through this function m, the distance between them expands by at most a factor of p times this thing. So what is this? If they're both 1, this is 1 plus 1 to some power. So So what I'm saying here is this guarantee you can think of as on the sphere, this map doesn't expand distances too much. And then there's this correcting factor that takes care of the fact that, well, here I'm raising to the power p, so things must somehow become worse as I like go out away from the origin. Okay, so for one thing I need for an average distortion embedding is that I don't expand distances too much. Like that's one property I need as a starting point. And here I almost have that, except it only works for the sphere. So how can I make sure I have this non-expansion property for like the whole space? And here's the simple fix. You just kind of make it true. So you create a new map, okay, which is kind of this Mazur map like redefined somehow, like rescaled. For this new map, I first take the point and I bring it to the sphere where I know things are nice. And then I scale the result by the actual LP norm of this point x. Okay. Which is the same, like, because this is like homogeneous to the power p, this is the same as saying I'll multiply the Mazur map by the LP norm of x to the power 1 minus p. Okay, but I think this is like the more informative way to think of it. I bring x down to the sphere, and then I scale back to like where it should be. Okay, now this is like a one homogeneous function, right? This, so I don't have this like technical problem anymore. And it's not a very hard exercise, like using this inequality to show that this now is Lipschitz, that it doesn't expand distances by more than a factor of like order p. By the way, I never explain my notation here, but hopefully it's intuitive. This means like there's a hidden constant that it's an absolute constant, doesn't depend on anything else. Like, I don't know, 2 or something like that. I think it's like 2 or 3. Good. Yeah, okay, good. So that's one important construction. By the way, what can we say now about the, should be obvious, what can we say now about the, if I apply this new function to some x, what is the L1 norm of that? In terms of the LP norm of x? Make sure we understand. So again, what did I do? I took x, I scaled it so that its LP norm is 1, applied the Mazur map, and then I multiplied by the LP norm of x. So the L1 norm of this is just the LP norm of x. I guess, sorry. I guess just from the definitions, let me do this. Okay, from the definition of this m tilde function, good. But the second thing is just 1, right? So this is just the LP norm of x. Okay, so my claim is that this will be more or less my average distortion embedding. It's not quite, it doesn't quite work, but I need one more element. But at least it achieves one thing, right? It doesn't expand distances too much. So far, so good. Good. So a bit of a, okay, slight I don't know, is it a tangent? It's not a tangent, I need it. A bit of a detour, like what looks a little bit like a detour. So now I need to worry about the average distance not going down. Okay, so for that I need like a simple technical, like little technical tool that probably familiar to many people, something about geometric medians. Okay, so basically I need this inequality. Let me give you with a picture what it's saying. So I have some points somewhere, okay? And I have these inequalities. So what am I claiming here? I'm claiming that if I fix any point z, so let me fix some point z, and I look at the average distance of z to every point in P. Okay. Right, so first I'm claiming that this is never much less than the average pairwise distance between like two random points in Z. Okay. So I'm comparing two things. I'm comparing average distance to a fixed point Z versus average distance between pairs of points in my points at P. Okay. I'm saying if I take the point Z that minimizes this average distance, this is the geometric median, then these two things are the same up to a factor of 2. Okay. And we can show this. It's just the consequence of the triangle inequality. So intuitively, right, these two things are the same. If I pick Z to be like really somewhere in the middle of this point cloud, if Z is way far out, you can imagine that the average distance to Z could be much bigger than the average pairwise distance between points in P. Okay. I'm talking about geometric median because the point that achieves this minimum is called a geometric median. And like, if the distance is like the only sensible distance on the line, so like the absolute value on the line, then it is achieved by like the median of the points, or like one of the medians of the points. Like median now in like the usual sense of like, you know, the middle point. Okay, good. So these inequalities are actually pretty simple. So to go from here to here, it's just that here I'm taking the average distance to a point that minimizes this average distance. And here I'm taking the average of average distances. So just minimum is smaller than average. This is why that inequality holds. The other one, does anyone see why that one holds? This is really saying that this is smaller than the average distance to any point. And that's just because of the triangle inequality, right? So from triangle inequality, you can just say this is at most. Sorry, and here's the size of P, by the way. I should have said that somewhere. So from triangle inequality, I know that this is at most this. Okay, and now if I just open the parentheses and like do the calculation, I see I get the bound. Okay. Good. All right. So now we have what we need for the embedding. Here is the average distortion embedding of LP into L1. Like, I can put things together now. I take a point T that I'll choose in some way. Let me ignore how I choose it for a second. Okay. And now the embedding is just this map, this like rescaled Mazur map that we just talked about, applied to the points X, but shifted by T, okay, to X minus T. So that's the embedding. Good. And the claim is this is an, okay, good, sorry. And let me now say how I choose T. Okay, so for LP, the choice of t is actually quite simple. I choose every coordinate of t to be the median. So again, remember I'm constructing an embedding that doesn't decrease the average distance between points in some set p. Okay? So I'll choose every coordinate of t to be the median in the usual sense of median of numbers of the ith coordinates of the points in P. Okay, so I take my point set, in every coordinate, I just project all my points on that coordinate, take the median, that's Ti. And now I do this for every I, this gives me T. I shift everything by T. Basically, to put it a different way, I shift all the points so that the median of the points in P is the origin. So let me write that, because I think that's a bit more intuitive. Okay, so we shift so that the median of the shifted points at P is 0 in every coordinate. Now I'm talking about median in the usual sense of median of numbers. Okay, and the claim is this is an embedding of LP into L1 with average distortion at, on the order of P. Okay, and the main observation here is that now once I apply this map, remember. Okay, so what am I applying? I'm just applying this scaled Mazur map. Remember, the Mazur map preserves signs. And now I just kind of rescaled it by some non-negative number. So this also preserves signs. Okay, so because it preserves signs, 0 is now still the median. In other words, in every coordinate, the median of this map point set is still 0. Okay, but now in L1, this is also the geometric median. So here, when I say median now, I really mean geometric median. So basically, I made sure that the origin is the geometric median of my mapped point set. Okay, which is where I used the previous inequality. Okay, so now I can basically finish the proof. So just make sure that. So what do I need to make sure? I need to make sure that the average distance stays large. Good. So let's see what it holds. Again, I'll use n for the size of the size of P. Okay. All right. So I have this average distance. I want to make sure that it's not much smaller, or not much smaller than the average distance between points before I map them through F. Now, good. So now, because 0 is the geometric median of this map point set, I know that this is at least the average distance to 0, right? But the average distance to 0 is just the norm of Fp of x. Sorry, this norm is 1 here. I should keep track of which norm is where. Okay. Good. But now I know this rescaled Mazur map exactly preserves distances to 0, right? So I know the norm of this is exactly the LP norm of that. So this is exactly right? Because the L1 norm of the Mazur map is the LP norm to the power P, and for the rescaled Mazur map, it's not to the power P anymore. It's just the LP norm of just the LP norm of what's inside. Okay, and now I just use the other inequality from the previous slide, which tells me, okay, this is now the average distance to some point. Okay, but that's always going to be at least the average pairwise distance, up to a factor of 2. Okay, so that's basically the proof. Like we lose a factor of 2 here, and we can just like scale up by a factor of 2 if we want. Okay, so yeah, that's the embed. Any question? This is like the main technical thing I wanted to show you. I have a few more slides to just kind of hint at stuff that I cannot show. If I have time for 3-4 minutes.
So what's the point set for which the rescale master map doesn't work without this translation?
Yeah, I think I would expect if like the point set is just kind of far from the origin, like it's all in the positive order, that should probably break. Alex. Yeah. Good. Okay, so let me say, okay, this like looks kind of special to LP, but it's not that special to LP. So what made this work? I'm claiming what made this work is that what was nice about this master map that made this work? It gave me a map, like a function from the unit sphere of whatever I'm trying to send to like L1 or L2 into the unit sphere of L1 or L2. Here I'm going back to like L2, although what I showed before was L1, but these things kind of work roughly in the same way. For this more general stuff, I think L2 is a bit nicer, so I'll go back to like mapping into L2. Okay, so what was nice about the master map? It sends the sphere to the sphere. It's nicely continuous. This is a technical thing. It's alpha holder continuous. So basically, it's like Lipschitz continuous, but you raise the right-hand side distance to power alpha. I won't write it precisely. And usually we need that the inverse is also somewhat continuous. Like how continuous the inverse is, I think, is like a little bit less important for the results, but you need something about the inverse being nice as well. So in other words, what you need here is what's that? It's a biholder homomorphism between the spheres. So this is this type of object actually has been studied a lot. So there has been a lot of work constructing these kind of functions between spheres that are nicely continuous and have continuous inverses. And whenever you have a function like that, roughly speaking, whenever you have a function like that, you can get an average distortion embedding from like this norm to L2. So if you have a nicely continuous function between the sphere of your norm and L2 that also has a nicely continuous inverse, then you get an average distortion embedding in a similar way to what I just showed you. So things just get a little more technical. I should say here some things. So typically here, this alpha holder continuous like condition maps to the embedding being of the alpha snowflake. You can spell snowflake apparently. Okay, and like there's an implied constant here, so basically the less continuous phi is, the larger the distortion is going to be. But there's like a result of this type that you can like state formally that is true. So this is a bit high level. Okay, so I'm not mentioning here like what spaces we know these things exist, but there is a lot that's known here. There's like results from the literature. People have studied this in functional analysis for different reasons, but related somewhat reasons, and you can kind of take maps off the shelf and just use them. Let me mention like one final thing, which is, okay, can we find such a map for any d-dimensional norm into Euclidean space? Okay, and in some sense the answer is yes, but yeah, in some sense the answer is yes. So what you can do is, and here like now I'm going to be very high level. So what you need to do, so for this kind of program to work for any d-norm space, like d-dimensional norm space, you need some map, like nicely continuous map between spheres of like any, the sphere of any norm into Euclidean space. That sounds a bit fishy somehow. But what turns out to work to some extent is you can kind of perturb your norm space to make it look a bit more like Euclidean space, and you can perturb Euclidean space to make it look a bit more like your norm space, kind of bring them a little closer together. And then you can find this nice continuous map that also has a continuous inverse between these perturbations. So now I'm doing things very high level, and you'll see also how I cannot draw things very well. But roughly you can smooth. Okay, this doesn't look smooth at all. Imagine. Oh, this is terrible. Okay, I'll try again. It's still terrible, probably. Okay, imagine it's a bit smoother, a bit more like the Euclidean ball. Imagine this one also looks a bit more like, your original space somehow. Okay. So you can perturb both, and then once you perturb them, you can find this nice continuous function phi that goes between them and kind of has a continuous inverse as well. And it has some continuity that allows you to show something. So at the end, what you end up doing is you take your norm space, you map it into some other norm space, let's call it X, which you then map into a different norm space Y, which you can map into L2. And the first mapping is really bi-Lipschitz. And the second mapping is also bi-Lipschitz. And this mapping in between is like an average distortion mapping, and is based on this like continuous function between spheres phi. Good. So roughly speaking, this is just the mapping to this perturbation. So it's bi-Lipschitz because this perturbation is still pretty close to the original space. And this is the mapping from this perturbation of L2 back into L2, which again, bi-Lipschitz because you just perturbed L2 slightly. The interesting thing here is the one between X and Y, where you can now find, like once you do this smoothing, you can now find this nice continuous map between spheres that you can use to build an average distortion embedding using kind of similar technology to what I showed you, but more complicated. All of this is based on like these like smoothings and finding these maps. All of this is based on complex interpolation. So like kind of a methodical way to interpolate norm spaces. So like find spaces that are between two spaces that I have given you. Okay, and I'll leave it on this high level. I'll just say something about what this gives you. So this gives you an embedding of some snowflake of our d-dimensional, our arbitrary d-dimensional norm space with average distortion, which is polynomial in log of dimension. The issue with this one is that the snowflake is pretty small, so this goes to 0 with dimension, right? And this ends up hurting you in applications. It gives you kind of bad approximations, for example, not as great as we would like when you try to construct data structures for approximate near neighbor search, for example. On the other hand, this embedding is somewhat efficient. So in the sense that after like a lot of work, we actually do know how to efficiently compute these maps, and we know how to efficiently embed a given point. The issue where this is not quite as efficient as we would like also is that this the argument still involves this t shift, and in this generality, this t shift is not as simple as taking medians in every coordinate. Finding this t ends up being difficult. So you kind of need exponential time to find the right t, and then once you do that, everything is efficiently computable. But finding this shift is basically, we know it exists, via some topological argument that's not really constructive. And then once we know it exists, we can look for it in exponential time, but we don't know how to really compute it efficiently. So this is almost efficient in the sense that, like I said before, finding the map FP involves finding the shift D, which we don't know how to do, but once we find it, everything else is efficient. Okay, and I'll stop here. Sorry, I think yeah.
Questions?
Yes.
So this is all in finite dimensions. What
Yeah.
do you know? What is there any work on like functional spaces?
Oh, sure. Actually, some of what we did, for example, in this work, is take theorems proved in like in infinite dimensions and bring them down to finite dimensions. Right. So. It's just that not all of there's definitely work in infinite dimensions, but some results just I guess cannot really have analogs because, for example, for Naor's embedding that I talked about, which is for any d-dimensional norm space, the distortion there was like grows with d. It's logarithmic, but it still grows with d, and that's necessary. So it's not clear what's like what would be a statement, like a corresponding statement in infinite dimensions. Here too, like this stuff that I said that I didn't really get into comes from some infinite dimensional result. But infinite dimensional result doesn't sound as general if I state it. Like it needs more, like it puts more conditions on the spaces so that you can actually show something. This result is kind of more general, but it's in finite dimensions.
So when you said that result about the half snowflake and the root log d, when you said it uses some duality, so you mean like you're going to the algebraic dual of the vector space, or is it duality?
Good. So I didn't say what duality means. I have a slide. I have one slide that I didn't show. So duality in the sense of convex duality, roughly speaking. So you end up showing. I won't try to like this slide. Maybe it's just going to be confusing. Should I? I don't know. I mean, I can leave it, but good. So you end up showing a statement that is also kind of on average. So what do I want to say? Good. So the average distortion requirement is that average distance doesn't go down, but all like no distance should increase too much, right? So I can have another requirement where I have a distribution on pairs of points, and ask that on average over this distribution, the average distance on this distribution doesn't increase too much. So I can like add one more layer of like doing things on average. Now if I do this for every distribution on pairs of points, that's kind of dual in the sense of convex duality of like LPs kind of stuff to the existence of average distortion embeddings. So basically I can write down the existence of average distortion embeddings as like a kind of some point being some convex cone. And I can say, well, if there is no such point, then there's a certificate, and I can show no such certificate exists. Yeah, so when I say duality, it's not really algebraic, it's more like, yes, like Farkas-Lemma kind of duality.
Okay.
Other questions?
So back to this definition, so we define it as nobody is allowed to expand, and the average shrinking is small. But now what you said about duality, so if I define the other way, so I allow you to expand how much you want, and nobody shrinks, and now look on average. So this duality will imply the same results?
No, I don't think so. So right, so the other definition, right? I guess it depends what you're taking the average over. So in average distortion, we really look at average distance between, let me find the definition now. Right, like here we're not looking at like kind of every possible distribution on pairs of points. It's really, I fix a point set and I just look at like kind of a uniform average over pairs of points. I think things become a little different if I say, okay, for any distribution on pairs of points, then like there should be some embedding, then maybe these duality results would imply something. So, for example, here, if I insisted this holds not just for any point set and this kind of product distribution, like over the point set, if I ask that this holds for any, like now any distribution on pairs of points in the metric, I think that's just bi-Lipschitz embeddings, like by the same kind of duality. But you can now ask, like, okay, what about, like, can I flip things? Can I make sure that no distance contracts and on average distances don't expand too much? And I think there's a reason this is not. Okay, so it doesn't seem to be what we need for approximate near neighbor search, but I think there are maybe also these kind of results won't hold if I make this relaxation. So
it seems that if you take the inverse of the snowflake, it would show a counterexample, right?
Yeah, I
This
think
never
the,
exists.
It can't exist.
I see.
There's no theorem because there's no theorem.
Yeah.
Okay, right, right.
Clearly, I mean.
Yeah.
But it would be enough for the research.
I will pin up in the same way. I see.
Enough,
But it just doesn't exist. Okay, sorry. Good. Good. Okay. Yeah, I knew there was a good reason. Okay, that's a very good reason, right? So there's not- right. Okay. Which is a bit, yeah. Okay.
It's not surprising.
Okay. Other questions? Thank you.
Yeah, thanks again.